Hello everyone, my name is Jelani and welcome to my channel that is dedicated to helping you improve and succeed at CXC Math. Now in today's video, the topic that we're looking at is some past paper revision in matrices, and the main objective is to look at the May 2016 paper, specifically a little bit of question 11, right? We're gonna look at just a small portion of the matrix questions just to sort of jog your memory on matrices. If you haven't seen matrices before, this video may not be for you. I have some other videos that introduce the topic of matrices and build your knowledge all the way up to be able to handle these questions. I could put those in the link in the description, or I could put them on top here. But for now, if you haven't seen matrices, this may not be the best video for you. But if you're just, doing some revision, maybe you have some exams coming up, or you just want to refresh your mind, this is the perfect video right here. So let's get into this question. First one says, to determine the value of x for which the matrix 3, x, 2, and 4 is singular. And this question is a very, very important type of question to be able to handle. The key word that we're looking at in this question here is the word singular. So let's have a quick recap. That a singular matrix has a determinant of 0, and therefore I'll just use the therefore symbol, and therefore has no inverse. So we're not going to stress too much on the second portion of this recap about the no inverse portion. What we're going to stress on right now is the fact that it says a singular matrix has a determinant of 0. So if we find our determinant of this matrix, remember the determinant of the matrix, if I have a matrix like A, which makes up of these components A, B, C, D, then the determinant of A will be equal to A multiplied by D, this diagonal, minus B multiplied by C, second diagonal here. So what this is telling us, when we have a singular matrix, what we have to do for our solution, right? So the solution now in blue for the question, we just have to find the determinant of this matrix. So let's give this matrix a name, right? Let's just call it let's call it matrix B is equal to 3, x, 2, 4. Then the determinant of B will be equal to A by D, let's just write in out the formula here, minus B by C. And if we do our calculations here, we're gonna get 3 by 4 minus x multiplied by 2. Just gonna erase this stuff in red here. If you need to see it, you could always just rewind or pause the video just to take down those notes. But just to get a little bit more space, I'm erasing. So now our determinant of B, 3 by 4 is 12, minus x by 2 is 2x. And because our matrix is singular, we know that our determinant has to be equal to 0. So all we need to do here is we just need to take 12 minus 2x equal to 0 and just solve this equation here. We just say, okay, we get minus 2x equal to negative 12, and x will be equal to negative 12 on negative 2. X will be equal to positive 6. And there you have it. That's the value of x for which that matrix there is singular. Now let's move on to the second question here. The second question in this 2016 past paper, it says N and P are 2 by 2 matrices such that N is equal to 4, 1, 3, 2, and P is equal to 1, 5, 2, 1. And they want us to determine NP. So this here is matrix multiplication. Now, like I said, I have a lot of videos before that go through matrices in depth. So if you need a proper refresher on matrix multiplication, I'll put those videos, I'll link them in the description of this video here. But for now, let's just go through this multiplication here. I'll just do it in a very summarized version of how we're gonna do this here. So the first thing we wanna do, right? We want to set up our matrices, how they're going to be multiplied. So we multiplying N by P. So let's write matrix N, which is 4, 1, 3, 2. And let's write matrix P, 1, 5, 2, 1. And what you always want to do before you start multiplying, I always suggest this, is that you perform the test for compatibility, which involves us just writing out the order of the two matrices. So the first matrix is a 2 by 2 matrix, and the second matrix is also a 2 by 2 matrix. And what the test for compatibility says is that if we draw a circle around the two numbers on the inside, those two numbers, if they are the same, then that means our matrices are compatible for multiplication. If the numbers were not the same, then that means the matrices cannot be multiplied. So here we have the same numbers inside the circle, so we all cleared for multiplication. But what the test for compatibility also does for us is the numbers that we did not circle, they tell us the order of our answer. So our answer is also going to be a 2 by 2 matrix. This is why the test for compatibility is so important. Because what we could now do is we could now take our answer and we could create a sort of framework to model our 2 by 2 matrix that we know is going to be our answer. So just to clarify on what I mean by that, what I like to do is I like to create these little boxes that we're going to place our numbers in when we're doing our calculation. So the box is kind of going to simulate what the 2 by 2 matrix would look like. And it helps as a guide to help you multiply the matrices without making too many errors. So now that we have our 2 by 2 matrix solution with the guide boxes, we're going to start to do our row by column multiplication. So we start off with the first row by the first column, and we say 4 multiplied by 1, 4 multiplied by 1, giving us 4, plus 1 multiplied by 2, giving us 2. Now we move on to the first row, second column, and so we get here 4 multiplied by 5, giving us 20, plus 1 multiplied by 1, giving us 1. So we finish with the first row of our answer. That means we finish with the first row of our multiplication. So now we move on to the second row, and we're going to multiply by the first column. So we go in 3 multiplied by 1, we're going to get 3, plus 2 multiplied by 2, we're going to get 4. Finish with this first column, so now we move on to the second row, second column, and we do the last bit of multiplication. We get 3 multiplied by 5, 15, and we get 2 multiplied by 1, 2. And so now we have everything nice and neat in our guide boxes. There's no way we could confuse what we have to add up now. And we just start to simplify. So we get here 4 plus 2 gives us 6, 20 plus 1 gives us 21. 3 plus 4 gives us 7. And 15 plus 2 gives us 17. And that is the answer there for our multiplication of n by p right here. So this brings us to the last portion of this question, which is on this next page here. It says, given that Pn is equal to 19, 11, 11, 4, determine whether matrix multiplication is commutative. Again, a very important thing here. If you know about this, then you don't even have to bother thinking too hard. You can just answer it immediately. But of course, I'm going to show it to those of you who may not be familiar with this. So in order to answer this question, let's just rewrite our answer from the last question that we did, which is that n by p is equal to 6, 21, 7, and 17. So what I'm going to do, I'm just going to grab it here and, oops. Right. Just copying it and I'm going to paste it on the next page. So this is what we just calculated. And now this question is telling us that p multiplied by n, if we look at the two matrices, they are very different to one another. And what commutative means in regards to math is it means that the order in which I perform an operation does not matter. So just to clarify on that, if I were to have 3 plus 7, then my answer is 10. If I were to change the order and put 7 plus 3, then my answer is still 10. So therefore, the fact that the order doesn't matter, I still get my same value of 10. It means that this here, addition, the operation, which is addition, is commutative. And it works with multiplication as well, right? If I were to multiply some regular numbers and I were to have 3, let's not use those same numbers, let's use some different ones. Let's use 4 multiplied by 2, then I get 8. And if I change the order and I say 2 multiplied by 4, then I still get 8. So multiplication is also commutative. I'll just put COMM just for short. But if we look at what we have here, we have NP. This is what we calculated the first time around. But when they switch the order to PN, we get different values. So the fact that we get in different values, we're not getting the same answer when we change around the order of multiplication. What it means, we could say here very confidently, we could say since n multiplied by p is not equal to p multiplied by n, therefore matrix multiplication, when you're multiplying matrices, is not commutative. And there you have it. That's the answer for this question right here. So now that we know that matrix multiplication is not commutative, we don't even have to think about it too much next time we see a question like this. We just need to remember, no matter what you're multiplying with matrices, the matrix multiplication will not be commutative. Once you change the order, you will get a different answer. Alright, so that brings us to the end of this video here. We successfully looked at a good bit of questions in matrices from this 2016 past paper. I hope this video was of help to you. I hope you learned something from it. I hope you enjoyed it. I just hope that you benefited some way from it. If you did, you could leave a like. If you have any questions, drop a comment. I'll be sure to answer it. And yeah, just appreciate you if you stuck around this far in the video. So thanks again for watching, and I'll see you in the next one.